All right, so this next section is 4.6 mean value theorem.
Come on, you heard the best part.
Hello and welcome to Calculus mean value theorem. Let's go. Tomorrow. Yeah. The stream started like a minute ago. We haven't done anything yet. Let's go. So, 3, 2, 1? Yes. Okay. Mean value theorem, I said. Let's go. So, yes. Welcome to Calculus 1. Mean value theorem 4.6. For the third time. Q-tips, man.
We got like 3 minutes on it already.
Yep. So, mean value. I know, mean value theorem. It's a very. What happened?
You're not energetic now.
You're not energetic?
Yeah, because you.
Where's your Red Bull?
Energy.
Oh, welcome to Calculus 1 4.6. There we go. All right. So 4.6. All right. Oh, Brian is here. Okay, we can start. Hello and welcome back to Calculus 1, section 4.6, mean value theorem. What an introduction. 5 minutes. Wasted. Waiting for Brian. It's all his fault. So the section is really cool. It is a way to connect the average and instantaneous worlds of change. So we know that the slope of the secant line is calculating the average, and the slope of the tangent line was the derivative, right? Was instantaneous. And we also talked about driving, and I said that if you are going from point A to point B and you drive, let's say it's 10 miles, and you get that place in 10 minutes, that means you are driving 60 miles per hour. But you didn't get into a car while car was going 60 miles per hour. You started at 0 and then definitely went over and so on. So when you are looking at a speedometer, it is instantaneous rate of change. So you look at the speed at the instant, and as you push the gas or the brake, it instantaneously changes. So that one, the speedometer, is the derivative. And you get ticketed for it if you go over the numbers that are suggested by law. No, I mean, proposed by law? No, what is the, yeah, mandated. All right, there we go. See, I just treated it as suggested.
When there's cops around, when there isn't, it's
suggested. So now we have the world of the mean value theorem. And let's consider a situation. So guys, observe this. Let's say this is a highway. And over here is a bush, shrubbery, right? Some kind. And then over here, we have a situation. And then there's another bush, shrubbery, let's say 5 miles away. With another situation. So they're measuring the speed in certain area, And what's happening is, as you are driving down this highway, you notice the first, right, because you invested in a detector, right? So you notice the first radar on, you slow down, you pass through the 55 miles per hour speed limit, you don't get pulled over, then you drive, then your radar detector goes off again, right, before the second one. You slow down, you go 55 miles per hour through the second trap, and the posted speed limit is 55, by the way, I forgot to say that. So no speeding tickets whatsoever until a few days, and then you get one in the mail. Now, usually when I teach Calc 1 class, someone admits that this happened. I don't know if it's going to be in this classroom, but almost always I have a student who said, oh yeah, it happened to me. So you didn't get the pull over, the ticket just came in the mail and said you were speeding, and then here's the ticket. Now let's see what's happening here. Hold on. So let's say that you went through the first trap at 1:04 p.m. and you went through the second trap at 1:08 p.m. So these were 4 minutes away, right? So you know what your average speed is. The average speed is going to be distance, change in distance divided by change in time. I heard you don't like these deltas, so I'm going to use that notation for that. And the change in distance was 5 miles. The change in time is 4 minutes, so 4 over 60, because I want that in miles. I want that in hours. So 4 divided by 60 would be in hours. And what you are getting is, oh, this is too crazy. 60 times 5 is 300 divided by 4. This is it's way too much, right? What? So you are 20 over. Now, why are you getting the ticket? You're getting the ticket because of the theorem in mathematics, which states that if f is continuous on a closed interval and differentiable on the open interval, that there's at least one point C in AB such that these two average speed is the same as instantaneous speed. You can only be charged for instantaneous speed, but this is the theorem that relates the two. And if the speed limit was 55 and 55, and the calculation came out to 75, right? There we go. So let's write the theorem, which says if f of x is continuous on closed interval AB and differentiable on open interval AB, then there exists at least one point C such that, and here's the big formula, f prime of C is equal to f of B minus f of A divided by B minus A. That's the formula. Now, We know that the path is continuous, right? We know also that there was the derivative everywhere because you had speed to your car, you didn't teleport anywhere. So all of the conditions of this stand, and it says that there is at least one f of c such that this average is the same as the change. Technically, what they're saying here is that the slope of the secant line and the slope of the tangent line are parallel at that mysterious point. So if you want to think of the graph that accompanies this to learn this visually as well, you have a secant line, which is your bf of b and af of a. And then parallel to that, you have the tangent line, and that tangent line is at c, f of c. So this is what's happening. The two slopes are parallel, therefore equal. So where is this used? Did anyone get a ticket yet? Easy pass. You pass through one gate, log the time for your account, pass through the second easy pass gate, and if the times work out, ticket gets mailed. So that only works for those who have easy pass, obviously. If you don't have easy pass, if you stop on the toll to pay the toll, then nothing, right? Because I don't know what to tell you. Maybe you want to have 2 or 3 and then swap the pass. I don't know. So, believe it or not, that's it for the lecture. The lecture says that there is a point where the derivative of the tangent line is the same as the derivative of the secant line. And yeah. Well, we're going to do 2 more examples of this. So we are first going to do the example where, you know, we just have just a basic calculation, and then we'll do another word problem. So we did 1 word problem already. So ln 2x so f of x equals ln 2x on 1 to e. And we want to find c, x equals c, right? At which MVT works. So what do we have? Remember that f prime at c needs to be f of b minus f of a divided by b minus a. Now look, you have your a, you have your b. So now, what's the derivative of ln 2x? 1 over x, because it will be, right, that and then 2 is canceled. But remember, you have to plug in c on this side. So that's the derivative, equals to function computed at b, so that's ln 2e minus ln 2 times 1 divided by e minus 1. You just plug everything in. So 1 over c is equal to, now this is ln of 2 plus ln of e minus ln of 2 divided by e minus 1. I really like this problem because it's so easy to compute. These guys cancel, ln2 minus ln2, and you get 1 over e minus 1. You flip both fractions, right? You have 1 over c is equal to 1 over e minus 1. So c is equal to e minus 1. That's the point. X equals e minus 1. At that point, the instantaneous and the average have the same value.
We'll see next year.
So one more example. Example 35. And then after that, lap time. It says running pace. Explain why, if a runner completes a 6.2-mile race in 32 minutes, then he must have been running exactly 11 miles per hour at least twice in a race. So what do we have? We have that the distance is 6.2 miles. We have the time of 32 minutes. And they want to know why the speed was 11 miles per hour at least twice. Same formula over and over again. Remember, this speed 11 is actually instantaneous. So we have the distance over time. This is the same as the cop card. And here we go with crashes. Okay, well, I never had a crash like this before. Yep. Let's see. Let's at least finish this problem. So 6.2 divided by 32 over 60 is 6.2 times 60 over 32. And when you compute this, so this is technically 62 times 6 over 32, which is 31 times 6 over, is that 16? So we are getting that the average speed is 11.625 miles per hour. Now, in order to reach that as the average speed, and you have to start from 0, right? That's how every run starts, with runners, right, in that crouching position. And if the person with a gun misses them, they get to run. So we have the situation where a runner would start at 0 miles per hour, run, and then stop at the end of the race, again at 0. So if the average rate running was at 11.6, then 11 elevation is at least twice. Now, you know, it could have been certain, you know, dips in a road and stuff like that, like for racing, let's say, if you are racing a car and then on the track you have to slow down for certain bends and so on, you would go below average, and then you might have more of these. But you can clearly see from the graph why there are at least two that are 11, because you have to exceed that to get to 11.6, and then you have to go back through 11 to get to 0 because you stop. The race is over. You don't start racing and then race forever, right? You have to stop at some point. So that's the mean value theorem. Again, you are looking for the value C, and this problem 20 outlines the step-by-step solution, where the word problem at the beginning with cop cars and the problem 35 are technically the same problem. They now just have different flavors: inverse sine, inverse tangent, another e to the x problem, and so on. But they're all done the same way. You take the derivative, plug in c. On the other side, you have the average, and then you just work those out. All right, so that's the mean value theorem. Next class, we will be working on L'Hopital's rule. Let me just say bye to the stream.